Okay, all right, this is take 3. Okay, I'm talking about continuity. Let's see if I can blow that up a little bit. Continuity is when a graph is continuous and there's no breaks in the graph. You don't lift your pencil up or pen when you're graphing it. Here we have what's called a removable discontinuity. I've got two types. And basically, you've got just a hole here where, like in this case, -2 is not part of this function, but it's part of a different function. But here I have just a hole, it's a removable, and it continues on. And this hole could be filled by just like a plug. That's a removable discontinuity. Here's a case where we have maybe two functions. We've got this function that has all real numbers except for -2, and a different function that includes -2, perhaps. So in this case, my domain could be all real numbers where I have something different for -2 here. But notice that since I have this graph, obviously there's inputs all the way across the x-axis, so I have all real numbers. This -2 here is taken care of by this hole here. But this is a removable discontinuity. Here's another one where it's just a hole here. It could be filled with a plug, but here my domain isn't all real numbers. It's everything but maybe this point. Let's say it's -2. Okay, so that's a removable discontinuity. The removable discontinuity can come from maybe where originally in your function here, notice I can't have -2 in my denominator. That'll create 0 in an undefined function. But I can factor this difference of squares as x plus 2 times x minus 2 over x plus 2. And notice these x plus 2, these two factors will be crossed out, and I'm removing that discontinuity. So instead of having a vertical asymptote saying that I can't have -2, I'm just going to have a hole here. This is where normally you get a removable discontinuity from something that can be factored out. Originally in the equation you can't have it, but you're not going to have an asymptote there because it's removable. Okay? This is what's called a jump discontinuity. Okay? A jump discontinuity probably would come what's called a piecewise function, where I have one function for a domain from -infinity to here, and another function from that same point to infinity. Okay? Again, my domain would be probably all real numbers. Notice that everything's taken care of. I don't have anything for this hole here, but let's say that's -2. -2 is an input for this part here because there is a solid dot there. Okay, but that's a jump discontinuity where it just kind of skips up and the graph continues. But it is discontinuous. You had to lift your pen up. And here's an infinite discontinuity where we actually do have the vertical asymptote and the discontinuity is infinite. Okay, this is the parent function of 1 over x, but shifted to the right -1. 1 over x minus 1. Instead of the y-axis being the vertical asymptote, it's x equals 1. But there is a vertical asymptote because we can't have 1. That would create 0 in the denominator. But this discontinuity is infinite because that vertical line is. Okay. Now let's talk about increasing or decreasing functions. Kind of common sense. Between any 2 points, as my x values increase, if the output of x, function of x, increases, I have an increasing function. So as x increased from here to here, my f of x, my output, or y, increased from here to here. That's an increasing function. Obviously decreasing, well, let's just say that back. Take that back. Something within a function, something between 2 points. This is taught between 2 points. Between these 2 points, obviously this is increasing because as x increased, f of x increased. So in a graph, it's decreasing between any 2 points in an interval, which I should be saying, any 2 points in an interval. So between any 2 points in an interval, as x increases from left to right, obviously here f of x decreases, so between these 2 points that's decreasing, okay? Now, not rocket science. And then obviously constant, for any 2 points in an interval, as x increases, there's 0 change. So as x increased here, there was 0 change in y, my output f of x. Okay? And what you'll have to do is analyze the graph, and notice from this graph I've got -infinity to -3. It is decreasing. Okay? okay? And then from -3 to 2, it's constant. So I write -3 to 2. And then from 2 to infinity, it's increasing, okay? So when we talk about what a function is doing or analyzing a graph, I'm saying what it is doing. Or if they ask me where it is decreasing, I'm talking about how do I track that? I track it on the x-axis. So from this is my y values are going down here from where? From on the x-axis, from -infinity to -3. It's constant on the x. From my y values are constant, but they're constant. How do I mark? Relay that information by tracking it on the x-axis from -3 to 2, and so on. Something that this textbook does that some textbooks don't. Notice how the -3, I get a bracket here saying it's included here, and I also get a bracket here saying it's included on this part. Okay, so some textbooks look at it as if there's no open circle, but we can include this point. Kind of we're breaking it down well from here to here, and then I'm almost like a separate when it's constant from here to here. Notice -2 gets, or I'm sorry, +2 gets brackets for the constant and gets brackets for the increasing. Some textbooks don't annotate it that way. If you give the bracket here, this is going to be a parentheses. If you give the bracket to the 2, saying they're going to, it's kind of like, hey, it's either, this 2 needs to be either with the constant part or with the increasing part. But this textbook, 50% of them say you could kind of do it this way. You could put it with both, it could go both ways. This 3 could be here or here. Or, okay, this -3 rather, okay? I'm not too worried about it, okay? As long as you can tell me where it's decreasing, constant, and increasing. Boundedness. All right. 7 minutes. Boundedness is an easy concept too, okay? Let's talk about this. This graph here is bounded below. Notice how it's going to infinity. There are no boundaries. This just goes up to infinity. Some number b, something would be bounded below. If you have a number, notice they annotate for bounded below as a little b, okay? If it is less than or equal to every number in the range of my function f, okay? So notice this little b is less than or equal to, it's the min value in this, in this, the range, the output, it is less than or equal to every output in this whole function. That means it's not getting any lower than this b. That's bounded. That's like a lower boundary, okay? It's bounded below, but it's not bounded above, okay? The little b is the lower bound, okay? Bounded above. This function here has no lower bound, but it is bounded above, and that's going to be capital B. If you have some number capital B that's greater than or equal to every number in the range of my function f, you have an upper bound. B is the upper bound, okay? All right, here's a case, next page, where I've got this graph here that it's what we call bounded. Okay, you have both an upper bound, capital B, and a lower bound, little b, then you're bounded. Okay, here's my graph. It's kind of going through, but it peaks out here at this b. That's my top range value, and this is my minimum value for this function. So this graph is bounded. It has an upper bound and a lower bound. Okay, here's a graph that is not bounded. Notice I'd have some vertical asymptotes here and here. It's going to infinity, going to infinity, going to negative infinity. There are no bounds, no capital B and lower b, okay? So those are some concepts. That's about it, about analyzing graphs, and we'll be talking about tomorrow. So that's it. Look for, hopefully more of you are watching my videos, and I will see you Monday. Tuesday will be kind of a CBA review. CBA's Thursday, Wednesday I believe is testing, okay? All right, bye-bye.